Whenever the chair tells me to start.
Hello. Now we can continue our afternoon session, and right now, Dr. Eric Linder will give a talk with our topic, Precision Gravity in the Next Decade.
Okay. Thank you very much for inviting me.
Thank you.
So this is very much a follow-up to the two previous talks. So Professor Song talked about large-scale structure and talked somewhat about tests of gravity, talked about growth, talked about the understanding the model of the universe. And Professor Shushkov went into the depths of different theories of gravity as you move away from general relativity. So I'm going to take elements of both of those and talk about what the prospects are over the next decade of really coming to grips with how does gravity operate on cosmic scales, how do we test the framework of our cosmology to make sure that we're approaching it in the right way. So in the next decade, we have a very rich array of experiments that will be coming online. Young-sun mentioned the DESI instrument, the dark energy spectroscopic instrument, which is covering a wide area of the sky, as he said, an increase by a factor of 10 in the number of galaxy spectra that we have, mapping out the three-dimensional universe. LSST is doing this wide, deep imaging with a repeated survey of the sky, also picking up the transient universe. And then in the middle of the next decade, a satellite, WFIRST, which will do what is done best from space, doing the very deep spectroscopy, looking at the supernova distances, looking at the three-dimensional clustering as well. And in addition, there are the cosmic microwave background experiments that Professor Tajima talked about, going after really the primordial fluctuations, but as he also pointed out, you get gravitational lensing from the structure in the recent universe. And you can use that gravitational lensing to learn a lot about the properties of the recent universe. So I'm going to talk about three different approaches to how gravity affects things on cosmological scales. And I call those the push, the pull, and the wiggle of gravity. So I'll start off by talking about cosmic acceleration. This was the discovery that really brought this subject back into the forefront. One of the greatest mysteries in science. Why is the universe not decelerating under gravitational attraction, but it's expanding faster and faster in a way that seems opposite to our normal intuition of what gravity does? So cosmic acceleration. So I call it the push because, again, you think of gravity as pulling things, but now we're going off in the opposite direction, this expansion. The pull of gravity, very similar to what Young-sun talked about, the growth of structure and how rich that data set is in learning about the universe. And then something somewhat new that I wouldn't really have been talking about a couple of years ago, because we've just realized how important it is on cosmological scales, that gravitational waves, what field theorists would call the tensor sector of the theory, instead of the scalar sector, the density sector, is really on a par with the large-scale structure that we see directly. Actually probing the ripples in space-time can be immensely powerful tools. We're not up there technologically yet, but as we look 10, 20 years down the line, I think it's going to be a very rich field to work within. So here is everything you need to know about cosmic acceleration on one slide. Basically, when you talk about the expansion rate of the universe, the scale factor is a function of time, A of t, that carries all the information on the expansion you need. If you know the function, then of course you know its derivatives. Its first derivative is the Hubble expansion, the second derivative is the acceleration, and so forth. And those are written in terms then of components. You can say, I know there's this much matter, I know there's this much radiation, and everything else that I don't really know what it is, I'm going to call dark energy. And by knowing that expansion function A of t, that's the same thing as knowing a dark energy equation of state. How does it respond to if you have some pressure, what is the energy density that's associated with that? Okay. So what we can either phrase it as scale factor of the universe, or we can phrase it as the equation of state of dark energy. Einstein this is the century mark of his great theory, talked about a cosmological constant where this is exactly -1 for all times. So that's a very special case. And the amazing thing is that observations seem to point to that case. We want to test it more, but W equals -1 seems consistent with all the data that we know. But we can test that more. And in particular, what we found is that when you deal with sort of canonical, minimally coupled scalar field theories, so a material form of dark energy, that you can parameterize this in a very simple way with basically two parameters. What's its value today, and how quickly does it change over time? So Einstein's cosmological constant doesn't change over time. Here A is the scale factor. So WA is 0, and it's -1 for all times. Okay. This form is not gotten by just saying, what's a simple thing I could write down? It's gotten from the physics. The scalar field obeys a Klein-Gordon equation, and you look at how can I approximate the solutions in a simple form. And this works to the 0.1% level. And so you don't have to go into more details. We've basically figured out how to parameterize cosmic acceleration. But as I'll point out in my talk, that's just one small piece of what we want to know about the universe. So that was the push of gravity, the cosmic acceleration. And actually, I'm going to come full circle back at the end of the talk and actually go into a little bit more detail on the observational aspects of that. Now let's talk about the pull of gravity, this growth of cosmic structure that we've heard about in the talks. And you'll see some very familiar figures that I think Young-Sun has shown versions of us already. So general relativity is this amazing theory in that it's so highly predictive. If you know that cosmic acceleration, then you know the cosmic growth as well, the growth of structure. The two are completely tied together within general relativity. There is no extra freedom that you can really add to it. And so if we measure cosmic growth and we compare it to cosmic expansion, we can look for a consistency. Does it obey the laws of general relativity? And so here's an example of the growth rate versus redshift versus time. And here are data points from a number of surveys. And then here are three colored bands. And the middle band, the blue band, is the general relativity prediction, together with the cosmology as found by Planck. And first glance, you look at this and say, all right, yeah, it's reasonably consistent. But if you stare at it a bit more, you may start to get a little worried and say, most of these points really seem to be below the blue band. Not many of them are really above it. Of course, the error bars are large, so we don't get too worried. But for a theorist, theorists like to take tiny suspicions and blow them up into these giant theories and write 10 papers on it. So I think an observer would say, wait for the next generation of experiments. But theorists are saying, well, what am I going to write about tomorrow? And so there's a lot of work asking, is growth suppressed relative to general relativity? And what sort of theory would give that to us? And what predictions can we make that the observers then should go out and look for? And as Young-Sun pointed out, we interpret the data usually within either a linear theory or a perturbative expansion. And perhaps we simply have not been sophisticated enough in using that because the real universe is nonlinear. There is clustering that is beyond the linear regime. And Young-Sun talked about very, very substantial progress that's been made on that. And maybe once you do it completely correctly, then you'll find that this sort of 1 sigma tension will really go away. But we can also talk about this in a more sophisticated way. So this deviations from gravity here is parameterized by this gamma parameter, which is related to the growth rate in this very simple way. You take the matter history and you just raise it to the gamma power, and within general relativity, that gamma power for universes like ours take on this 0.55 value. And you can just ask, is gamma near 0.55, or is it 0.42, or is it 0.68, or whatever it is. And even though all these points look a little bit low, so it looks like gamma should be a little bit higher, when you take the most recent data, so this is the the DR12 data, the data release 12 data of BOSS that Young-Sun showed as well, and you ask what value of gamma do you get from that latest data together with the Planck satellite data. You find it actually lies right on that 0.55 value. It's very consistent. So the more modern data, the more sophisticated the analysis, you tend to, again, see very good consistency with general relativity. But suppose we want to go beyond that one number, that gamma parameterization. For one thing, we know that gravity not only affects the growth of structure, but it also affects the deflection of light. It affects gravitational lensing. And we have measurements of the effects of gravitational lensing on the images in the sky. And so we can instead say, how does it affect the growth of matter, and how does it affect the propagation of light? We can split into two different parameters, and then ask, are they both the same, the way they should be in general relativity, and are they Newton's constant, the way they should be in general relativity? So we're going to call Newton's constant 1, and we can see that the growth of structure, this DR12 analysis, gives us this band. It's completely insensitive to the value with respect to light because it's measuring growth, and it's pretty close, consistent to 1. And then we can also use lensing analysis, and this is cosmic microwave background lensing from Planck, and that cuts off at a different angle. So we end up with a nice, reasonably tight contour, a few percent contour. And that's blown up in this figure here. And here you can see the horizontal and the vertical dashed lines. The cosmological constant lies right there, within the 68% contour. So again, there's no evidence that says there's any problem with general relativity. But let's again be a bit more sophisticated. We've gone from this one parameter to two parameters, but that's assuming that they're constant in time, that they don't change as the evolution of the universe changes. Let's try to elaborate on that a little bit. So let's let them change linearly in scale factor, or let's let them change basically proportional to the evolution of the matter density. So basically as a cubic power. And again, the intersection of the dashed lines is general relativity. So here it's consistent, and in this analysis it's consistent. But look what's happened to our error bars. Here we were getting, a couple percent. Now we're up to sort of 10%, and now we're up to about 40%. So depending on how much freedom we allow the gravitational variations, you can either say we're very confident that it's general relativity, or you can say we're going to need better data coming from future surveys. And so that's an important lesson. We have the ability to test gravity on cosmic scales, but be very careful about your model assumptions along the way. So here we're now dividing up how does gravity act in redshift bins. We're not going to assume a functional form. We're just going to say, let's fit it at low redshift, at middle redshift, and at high redshift, and see, are they all consistent with general relativity? So it's a very agnostic approach where you're not assuming any particular function, you're not assuming any particular model. And again, we see general relativity is within the error bars. Okay. One caution when you do, so I think this is a very model-independent approach, and it's my favorite approach because I don't believe any of the models. Some of the models are very beautiful theoretically, but they're not as beautiful in my mind as general relativity. And so we shouldn't believe them too much. And then over here, we take a particular class of gravity models, scalar tensor models. And scalar tensor models you can talk about in terms of these beta parameters. And what you find is, depending on the priors that you set on how much time variation there can be, you get very, very different answers. So even though they're all consistent with general relativity, if you assume you know exactly what the time variation is, in this case that it goes linearly with scale factor, you get this tiny little contour. But if you say, well, it's got some power law, I'll say the functional form is a power law, but I'll let that power be free between 0 and 3. I don't know if it's constant in time, I don't know if it's cubic in time, linear in time, then you blow up to this green contour. And if you say, I don't know what it is between 0 and 10, you blow up to this gray contour. So again, you have to worry about your theoretical prejudices when you're trying to fit gravity. And that's why I tend to prefer these model independent. If you go further in detail, so here we're dealing with an f of r theory, such as Professor Starobinsky talked about, then this B0 parameter, sometimes called the scalar, it's related to the scalar on mass or the Compton parameter, then you can get fairly tight constraints. So it all depends how much you want to focus in on one specific theory here, a class of theories here, or if you want to be completely model independent. Remember, we started off by saying general relativity makes this very strong prediction that whatever you get for the cosmic expansion tells you already what you have to get for cosmic growth. And if your data disagree between the two, then something's either amiss with your data or with your theory. And so instead of looking at them one by one, suppose we look at them jointly. And so this sort of a diagram looks at the growth rate and the expansion rate, the Hubble parameter, together. And now let's look at the behavior of a whole bunch of dark energy models. They all lie in this band, and they have this sort of characteristic wiggle at fairly low redshifts. Okay? Now let's look at some modified gravity models in this plane, and you see they also have a wiggle, but their wiggles go very far to the side, outside of this band. I've put some of the same models over here. So that's a signature of modified gravity in this expansion versus growth plane, without assuming any particular theory of modified gravity. All you're doing is you're plotting your data in terms of the growth rate at some redshift and the expansion rate at some redshift, and you just build up with your survey, you just build up at many different redshifts, you trace out one curve or another, and then you ask, what is the characteristic sort of wiggle pattern that you get? And these error bars here are the projections from the DESI survey that Young-Sun showed for how well you can do in measuring expansion and growth. So you can see those are 1% measurements, and those will be extremely revelatory about the type of theory. We'll be able to distinguish very clearly different dark energy theories, but we'd also be able to distinguish modified gravity theories from the dark energy scalar field. So as we get better data, we'll have many types of theoretical analysis, but this is one that I like because it really tests that consistency that general relativity says has to be there. The group from Kasi, led by Young-Sun, came up with another version of this, which I also think is extremely visual. It's very easy to see, where he isn't even assuming a Friedman-Robertson-Walker equations for how the expansion has to behave. So it's testing the actual model framework. So here you can measure expansion, and now you can also measure distances. So Friedman tells you those two are related. Distance is an integral of the expansion. But now we're saying maybe Friedman, let's test Friedman, let's not assume it. And we can see the relation between those. Let's look at the growth in the velocity field, the growth in the density field. And you can do all the permutations, growth in velocity versus distance, growth in velocity versus expansion, and so forth. And what they found in 2015, using what was then the best FOSS data, is, again, the x's basically mark the general relativity result. And you find consistency in all of them. And you're finding sort of 10, 20-ish% errors with current data. And so that's pretty impressive that we can already test gravity on cosmic scales, which you think of as this huge extrapolation from solar system scales. So in the future, with the surveys we get, we really will be able to make precision tests of gravity in a model-independent way. So you're not just going to get a result and say, well, but who believes that model? You'll be able to actually test the model framework. So let me move, in some sense, to the next area. So cosmic acceleration is, again, this thing that puts this doubt of Einstein relativity in our minds. Is general relativity right? Or is this new component, a new scalar field, or something else? There are many different aspects and avenues of research. And this is one of the main theory focuses at ECL, looking into both the dark energy models, the modified gravity models, but always with that mindset of we really want to see how it affects the observations. We want to extract the data from the observations. If you look at the general theories, such as Professor Shishkov talked about, the Horndeski theory, then you find that you're not only dealing with the expansion history, but you actually get 4 extra functions that enter in there. I don't know, did you go through the numbers of... Yeah, okay. So what you...
I mentioned this.
Okay, so if you do an effective field theory approach, or if you work within the Horndeski Lagrangian, you find 4 extra functions besides the expansion history. And cosmology suddenly becomes 5 times richer. That now there's these 5 things that we really want to understand. And here are these 4 extra things. One is the kinetic structure of the theory. One is basically, is the Planck mass a constant, or does it run with energy scale? One is a braiding between different sectors of the theory, and the other has to do with the tensor propagation speed of the tensor perturbations, gravity waves. Is that the speed of light? And so these 2 parts have to do with the tensor sector, not with densities. And so suddenly the tensor sector is equally important to the densities and velocities that our galaxy surveys are doing. So now, again, cosmology becomes so much richer that we now want to somehow probe gravity through gravitational waves as well. And that this will tell us some fundamentally new information. So as I said, we now have the tensor sector. And in order to understand what's going on, we need to understand the types of theories of modified gravity there could be. We need to be able to compute what are their implications for the observations. And of course, we need the data to then refine the theories, to test the theories, and to say, is general relativity the one and only theory that passes all these tests? So as I talk about the tensor theory, this is what I call the wiggle of gravity, the waves in space-time, the gravitational perturbations. So it's become very popular in the last few years to think of effective field theories. An effective field theory is a way of, again, being somewhat model independent. Instead of working with a very specific Lagrangian, you basically accept all terms in the Lagrangian that are consistent with certain symmetries that you impose on the problem. And this is, it's a technique that's been around for a long time, used extensively in quantum field theory. It's used in study of dark matter and in inflation. And here specifically, we're talking about it in terms of cosmic acceleration, dark energy. So these are the 4 functions, or it's a way of writing the 4 functions I mentioned in the Horndeski theory, that you have these different properties of how you mix sectors, how you change the kinetic structure. And there's this very nice paper by Bellini and Savitsky that talk about these property functions. And in particular, I'll be interested in the wave speed of gravitational waves. Does it deviate from the speed of light? So let's start off by asking, do we have a really simple way of writing these functions? They're functions of time. Okay? We're very bad at fitting functions of time with data because there just isn't that much data, isn't that precise. We're much better at fitting parameters. So you want to take that function, figure out its functional form, figure out what the parameters of the functional form are, and try to fit those. So that's what we did with cosmic expansion. We took the Hubble function, h of z or a of t, and we condensed it down to basically the matter density, the equation of state today, and the time variation of the equation of state. So now we're fitting 3 numbers instead of an entire function. Can we do that for gravity? So here's one of the simplest modified gravities you can write down, a 1-parameter f of r model. And this is what the running of the Planck mass looks like. So if some of you are bright mathematicians, then maybe you can immediately see, oh yes, there's a very simple functional form that will fit that. And then as I change the parameters in the theory, or as I change the theory, you'll be able to also fit that all within a framework. But I haven't been able to do that, and no one else has been able to do that so far. And so this idea of taking a function of time and reducing it down to a few numbers, which was successful in the expansion history case, right now we're sort of stymied by that in the gravitational case. But we have these other handles on gravity. So as we move into the nonlinear regime, we have strong density perturbations, then you get screening mechanisms that operate within gravity. So we know in the solar system, it looks like general relativity. How can you have modified gravity on cosmic scales and not in the solar system? People have come up with a series of screening mechanisms that basically freeze out the extra degree of freedom. as you get to either high curvature regimes or high derivative regimes and so forth. And so we can look for those sort of screening processes in the universe. We can look at the gravitational wave sector, and then of course a very direct way of probing the nature of gravity is looking at strong gravity regimes, studying black holes. So I'm going to focus here on the gravitational wave sector because that's really on cosmic scales. This is on sort of galactic to stellar scales, and this is on black hole scales. But again, I find it amazing that we have this synergy between these very different aspects. Cosmology is not cosmology, astrophysics is not on its own, and gravitational wave detection isn't on its own. We see this beautiful tie between all of them if we really want to understand our universe. And so, for example, as we look in cosmology, we look for gravitational waves, signatures in the microwave background. We look for gravitational waves through the dispersion and pulsar timing. And we try to detect gravitational waves directly through advanced LIGO, through CAGRA, through future experiments, LISA, and so forth. These are all different windows on gravity. And we want them to all work together. We want them to use them all. And so the future galaxy surveys have this deep complementarity that we really didn't understand as of a few years ago with the microwave background surveys and their approach to gravity, and then these astrophysical surveys looking for gravitational waves directly or through pulsar timing. So the microwave background is what I'll focus on here, again, because it's at cosmological scales. And so I traveled to the Atacama Desert in Chile, 5,200 meters or 17,000 feet. And this is one of this microwave background experiments, the polar bear experiment. And the Atacama Cosmology Telescope is right next door. And the wonderful pictures that we saw of Alma this morning, they're just along the valley from that as well. Chile actually set up an astronomical preserve. It's like a national park for astronomy. Very forward thinking, very, very interesting. And again, in the microwave background, we're trying to look all the way back to the inflation scenario, 10 to the minus 35 seconds after the Big Bang. We're really looking for the fluctuations of space-time itself as this violent process, this high-energy process happens. And these are such high energies, it's 1 trillion times more than what we can create on Earth in the particle accelerators. And so you're really testing fundamental physics at these energies. So as I said, this is one of the research thrusts here at ECL. And Mikhail is there, okay? He's giving the next talk, but this is some of the early results that he's got on all the CMB experiments in the world into one collaboration. In particular, the sites at the South Pole and the sites in Chile, to build this experiment to really go as deeply as possible using the advanced detectors that we heard about, the types of things that we've heard about. These experiments, they're talking about MKIS, they're talking about the transition edge sensors. We'll see what it ends up being. And this collaboration has already formed. They wrote a 200-page science book on what's all the great science that can come out of this, and the 200-page technology book saying this is the state of the art in detectors now, this is where we need to go, how do we scale up, how do we remove foregrounds, and all sorts of essential things like that. The community is not only interested, but private foundations have recognized that this is one of the most fascinating questions in science, trying to look back to that tiny fraction of a second after the Big Bang, the highest energies. And the Simons Foundation made a $40-some million grant to basically do a test bed for the stage 4 experiment called the Simons Observatory, which will be in the Atacama Desert in Chile. So, as I said, I was going to come full circle, so now let's go back to this cosmic acceleration. And let me now get very speculative and challenge some of the experimenters in the audience for a theoretical technique that's quite old. The theoretical idea is 50 years old, but the experimental techniques have not been up to that until I think the last couple of years. There's been a strong push. And so I want to hear from the experimenters about further ways of pushing this forward. So what's the theory idea? The theory idea was actually come up with by Alan Sandage and George McVitie in the early 1960s. The universe is expanding, and so objects, we can think of them as moving away from us. On the Earth, we would talk about a Doppler shift, a velocity away from us. Velocity being the first derivative. So we see a redshift. The frequency changes over time. But the universe isn't just coasting the way a car does with constant velocity. There's an acceleration. There's a second derivative. So if we stare at an object long enough, the redshift that we measure actually changes over time. The characteristic timescale is the expansion timescale of the universe, 10 billion years. We tend not to be patient enough to stare at an object for 10 billion years. So if you want to stare for 1 year, then that means you have to make a measurement at the 10 to the minus 10 level. This is why it's languished for 50 years. But as I say, within the last couple of years, there's been some interesting developments on both the theory side and the hardware side that say it's time to take a look at this again. We may not be ready for it, but we have to start thinking about how to make ourselves ready for it. So here's this redshift change over observer time, and it's directly measuring the Hubble parameter, whereas every distance we measure is an integral over the Hubble parameter. So it's a very direct probe of acceleration. We'd love to make this measurement. How well does it constrain our cosmology models? So here's again this dark energy plane, the equation of state today, the time variation. And you see, depending on what redshift you're making the measurement at, the direction of the constraint changes. And this low redshift case, the solid black curve, is very interesting because every other probe we have slants like this, left to right. Well, down, this way. Whereas this low redshift one slants the other way. And so it has this great complementarity with other probes. And if you can measure at low redshift, and you can measure at high redshift, for example with the CMB, then this contour shrinks down to this tiny little contour. You just have this wonderful complementarity. So if we could technically make the measurements, theoretically it's immensely powerful. All right. What are the problems? We want to measure something to 10 to the minus 10. If we know that anytime you want to make such a precision measurement, it kills you to try to measure it in an absolute sense. Trying to say, okay, what is that? Let me measure the frequency very exactly. That error bar was for 10 to the minus 12. you weren't supposed to ask. You've got to be ambitious. So you don't want to make an absolute measurement. So just as George's experiment was a differential microwave radiometer on COBE to measure the CMB, we want to make a differential measurement. And to make a differential measurement in frequency, we go back to Michelson and Morley. We go back to interferometers. So that gets you a lot of stability, but we also realize that instead of measuring the redshift of a line, looking at the frequency over a line over time, if we look at a doublet, two lines together, not only do they shift over time, but they spread out over time. And now we're making a differential measurement not of where they are in frequency, but we're looking at the frequency difference between them. And that's a measurement that has many advantages at canceling out systematics. So we want an interferometer that's measuring doublets, basically. And there were a lot of bright signals. So emission line galaxies that Young Sun talked about, they have these forbidden oxygen transitions that are these really sharp, really bright doublets. They're beautiful, beautiful things to try to look at. To partly answer George, suppose we completely fail, okay? We're not measuring cosmic acceleration. All the noises, all the astrophysical accelerations are wonderful science information. We're learning about how do stars bump along in the galaxy potential, this sort of rough potential. How do the forces in the local universe work? So in some sense, it's a no-lose proposition. If we can technically make the measurement, we'll learn something either about astrophysics or about cosmology. So why is a theorist who's been working a lot on modified gravity, what do they have anything to do with helping hardware development on this? So I've subtitled this, How to Build a Better Instrument with Modified Gravity. It was actually a very offhand suggestion. So we always have tea time, every Friday afternoon at Lawrence Berkeley Lab, where everyone from the physics division and around comes and they have their tea and cookies, and you just sort of get to chatting with people. And so I got to chat with an instrument builder, and he told me about this interferometer that he was building, and talking about some issues with stability. How do you calibrate the wavelength over time, which is exactly what we want to do. Because to get to 10 to the minus 10 or 11 or 12, we aren't going to be able to do it in one night. We will have to look over a baseline of 5 or 10 years. So how do you keep your wavelength calibrated over that? And I was thinking, in modified gravity, so we look at Horndeski theories, where does that come from? So originally it was first talked about in terms of Galilean theories, where you have a shift symmetry. You have a symmetry that protects you against quantum corrections. Okay, you have a certain translation invariance. Suppose you could imply that to the interferometer. And we got to talking and figured out you could absolutely do this. By changing the delay between the different arm lengths in a particular pattern, you basically give a certain shift symmetry, and this can cancel out some of the systematics. And so basically, a conventional spectrograph, if you make a small error in your wavelength calibration, it gives you a 1-for-1 error in your frequency measurement. Okay. His type of interferometer was what's called an EDI, an externally dispersed interferometer, which puts a Fourier transform spectrograph in front of a dispersion spectrograph. And so you get this extra modulation, which is called a whirl. It's like a Moiré pattern that you are imposing. And its reaction to a wavelength miscalibration is much, much smaller than a conventional spectrograph. And so that's a good start. But then when you apply our shift symmetry approach, you basically almost cancel it out. So he's actually built this, he's tested it, he wrote the journal article, it got on the cover of the Journal of Astronomical Telescopes, Instruments and Systems, and it demonstrated in the lab a 350 times reduction over the already good reduction. He took it to the Hale, the Palomar telescope, put it on there, and basically we're at the 10 to the minus 8 level. So we're still a long way from 10 to the minus 10 or 10 to the minus 12, but we're on the way. Why is an instrument builder interested in this? They may not care about cosmology or the redshift drift, because exoplanet studies want exactly these sort of measurements. They detect planets through the frequency shift in a star as it wobbles as a planet goes around it. And so they also want these 10 to the minus 10 measurements. And so a lot of the funding is actually coming from NASA for the exoplanet studies. And that's how he was able to build this and put it on the 200-inch telescope. So you have this wonderful synergy of the exoplanet community and the fundamental cosmology community. We have an opportunity here. And so I keep talking about this to try to get the excitement in the community to push this further. But that's how a modified gravity theorist can help build a better interferometer. So let me finish off. I think the future is very bright with all the data that's coming in from these surveys, that we really will get to the stage of precision tests of gravity. We'll be able to check general relativity, not just in the solar system, but really out all the way to cosmic scales. We have this extra richness to cosmology that we had not appreciated 5 or 10 years ago, where you don't only want to measure the expansion, you have to understand the growth, these extra 4 gravitational growth functions that enter in, and that the tensor sector, the gravitational waves, are an equally important part of understanding our universe. So here at ECL, we're using theory, we're using these advanced statistical techniques to deal with the data, and computation to test this out. Hopefully, the sort of sensor developments, the technologies, as well will help these CMB measurements to detect the gravitational waves and bring this all together and really get a beautiful picture of the universe. So if you are interested in any of these aspects, please talk to us about collaboration from the theory to the instrument side. And I'm very excited about these sort of investigations. Thank you.
Thank you. Very nice presentation. Any questions?
Okay.
So I didn't give you too much trouble on that one before, but now I have another question. If you really want to do this, why don't you do the calculations of using gravitational lenses to measure this directly, where you can have the same object with exactly the same gravitational redshift and have it combined in the same spectrometer so that you're measuring the two redshifts exactly at the same time in the same instrument, and you're using the fact that there is, 6 months to 10-year time delay in the gravitational lens,
Right.
and that gives you don't have to wait a whole year. You can get a 10-year time delay in a minute, right?
Exactly. So in the 2015 article that I listed up there, we have a section talking about that. And the answer basically comes down to statistics. We can get millions of these emission lines, but we can only get tens or hundreds of these gravitational lens systems.
The second aspect of that is if you think there's modified gravity, you're going to get a different answer in different gravitational lens configurations.
That's possible as well, right?
The complication might be that in gravitational lensing you have certainly you're getting a time delay of a few years, but you don't know the precise property of the lensing system.
Exactly.
So that becomes model dependent. Without having a very accurate knowledge of the lensing system, I think the method may not really succeed.
That's right. So the velocity of the source relative to the lens, or the acceleration of the source relative to the lens, gives you an effect itself. And unless you understand that well enough, so the way you normally get around that is you look at many, many lenses. And so it gets back to the statistics that we don't have the thousands of lenses to average it out. Yeah.
You think the acceleration of the lens?
So if you want z dot is an acceleration. So any peculiar acceleration contributes to that as well. So you want to average that away, and you just don't have enough lens systems.
How big does acceleration make this effect? If you're
bigger than 10 to the minus 10.
Exactly. No,
Yeah.
that's not right. Because if you're looking at something at a big redshift, so you're looking at the source at a redshift of 2,
right,
and the lensing system is at a redshift of 1, right?
Yeah.
How does I don't see the numbers work out that way.
Yeah, we originally tried to get rid of that 10-year observation baseline exactly this way, and everything we tried, we kept getting back to this issue of just you wouldn't have enough statistics to do it. If you had one perfect system, yes, it would be really powerful. But you have, as Pawan said, you have the uncertainty in the system itself, which you want to average out.
The other, may I ask, I don't know who is the next person, but may I just add to that, and also a related question is that both the lensing system is also moving, is not just participating in the general expansion, but it's part of a cluster of galaxy. Mm-hmm. It could be a galaxy or part of a cluster of a galaxy, and so the motion within, peculiar motion within that, it should be compared with the Hubble. So what you're thinking is that it at a redshift of 1, it has a high velocity. True, but it also has a relative peculiar velocity, which is changing on a short.
You're looking for
changes.
The change in the potential because of the motion.
Exactly right.
The change in the potential of the lens is likely to be small from the actual lens internal motion. And it's really the acceleration that can cause. The steady motion isn't going to make it.
Absolutely. So it is the acceleration, but the acceleration within the cluster, you see, you have to see how does that compete with V dot, or the changing of the Hubble constant. So that's what it comes down to.
Yeah.
And that's the study I'm assuming that you have.
It eliminates 2 systematic errors, right, and you get 1 new systematic error.
Yeah. Yeah.
Right.
No, ideally we
never do that well.
Yeah.
You eliminate systematic error, you use 2. So this is a big step forward.
Yeah.
You have it. So
Professor Zamani.
I have one other question, but I can ask it.
No.
I have a very simple question, which is that if you're asking to get a part in 10 to the 12th, the spectral lines you're looking at are certainly not better than a part in 10 to the 4 wide, probably more like a part in 10 to the 3. So you're asking for a very high signal to noise.
Right. So there's two things. One is, one of the aspects was because they're forbidden oxygen lines, you know the line shape basically. You couldn't just use any line for this because uncertainties in the line shape, how well you can centroid the lines are important. But because of this particular transition, you know the line shape, they're extremely bright. These emission line galaxies can be seen much further than just a normal galaxy. Yeah.
Please, one more.
Yeah.
So your ability to centroid is, the fraction of the line width is just the square root of the signal to noise ratio.
Right.
So
that's why the 10 to the minus 8 figure was 8 hours on Keck. You would like to do this with a 30-meter telescope. You want as many photons as you can.
8 hours on Keck for an exoplanet problem, and you're talking about detecting emission lines in galaxies. It's a different problem, different signal to noise.
No. The 8 hours was for the signal to noise of an emission line galaxy. Yeah. But as you say, we want as many photons as possible. That's the name of the game. Yeah.
Okay. Now let me shift to theoretical ethical remark. Of course, with description of using parameter gamma or ECPL parameters W0 W1. It's of course it's an approximation. So of course we can use it as far as our data are not excellent, but really one should still keep in our mind that all these parameters are not exactly constant, and in particular, it just that using reconstruction method similar to that reconstruction about which I spoke in my talk regarding inflation. In particular, it can be proved that gamma equal to constant is not possible for exactly constant is not possible for any quint essence models, and there was a recent paper by Podolarsky and myself in the same refers to W1. Even in the best case, it appears that they are good as far as we are speaking only about what happens at present and in the past, but this approximation will break down in the remote future. So once more, if you are satisfied that our theory is good at present and in the past, even it is okay. But if you want to make predictions for a remote future, it will not work. And simply, in particular, it is even clear when you write this equation of state, when you have the term W1 multiplied 1 minus A, as far as A is less than 1, all is okay if W1 is small. But if you consider infinitely remote future, when 1 minus A becomes as large as possible, negative, and when multiplied any possible W1, you will obtain arbitrary negative equation of state.
Yes, I agree completely. Any parameterization has limited applicability. You have to make sure not to extend it beyond that.
Okay, many thanks, Professor Eric Wheeler. Sorry, we have late. Now, Dr. Mikhail Deneze will give a talk, and his topic of his presentation is probing modified gravity impact on large-scale structure with next-generation survey.
Oops. Надо обучить, что ли? Нет, нет. View presentation. Control. Control. Full screen mode. Okay. So, okay. Okay. So I assume you hear me well. So today I will be talking about the probing modified gravity impact on large-scale structure with next-generation surveys. So this project we did at the very beginning of the year, and we continue working on that. So let me start with, so what are the next generation, so does it work? No? Okay, just a second. So I handle everything myself. Oops. Good. So now, good. Okay. So with, so the next generation surveys are, so there are ground-based and also space-based telescopes which will map the. So these surveys will, among them, Large Synoptic Survey Telescope, Dark Energy Survey Instrument, Euclid, and many others. So what these surveys will create the detailed map of the universe, the large-scale structure of it. So and both deep in space and time. And so the main goal is to test Einstein gravity. So, but if we formulate it in a bit different way, so whether so the surveys promise an unprecedented precision levels and also the huge amount of data, and we're interested whether we can use this data for looking for signatures of modified gravity. So, and as we are also interested whether we can find a simple parameterization so we can relate the modification of gravity at earlier times to the observables we measure today or at low redshifts. So and also whether so you know that there are so many models that could possibly describe the data. So and it will be also interesting whether we can find some way to distinguish between classes of the models to resolve some degeneracy. So let me start out with a basic thing about the growth of structure and how it is related to the gravitational effects. So within the linear perturbation theory, there is an equation for the overdensities. So this equation describes the growth of structure. So there is a term that so the term that so the Hubble expansion is generally preventing the cosmic structure from growth, and there is also the second term is the so these two terms are competing. The Hubble expansion prevents from structure and gravitational attraction on opposite. To look at any differing angle, you can look at the Poisson equation where this overdensity is a source of gravitational instability. So if you have some regions with underdense underdensity, then this spaces becomes empty from later in time. And if you have overdense regions, then the attraction works this way that you have denser and denser regions. So this overdensity is a deviation from the mean density. And so what we are doing is that we modify this equation by introducing the modified gravitational strength in terms of G Newton and see what happens to the quantity called growth. Quantity described in growth, what happens to it and what kind of things happen to other observables related to the over density. So in particular, if we restrict ourselves to the meta-dominated area, so we start running the universe at the meta-dominated area, we can introduce the growth factor, which is proportional to the over density, and we introduce it in such a way so that it is normalized to 1 in the meta-dominated era. And so you can rewrite the whole equation in terms of the growth factor G, and then using numerical method solve it and see what happens to the quantities that describe the observables, which can be measured by these cosmological surveys. So, with these cosmological surveys will enable us to measure peculiar velocities. And these peculiar velocities are the velocities of the galaxies. So, the difference between the apparent velocity of the galaxy and the assumed velocity due to Hubble expansion. So, and the quantity which will be measured is the redshift distortion, and this is the product of the growth rate and mass fluctuation sigma 8. So the growth rate here can be written in terms of the over density or in terms of the growth factor. So, and now we want to build some kind of intuition of how these quantities, growth rate, growth factor, and redshift distortion quantity of sigma 8 are affected by the gravitational modification we introduce in our work. So if we rewrite the previous equation here in terms of growth factor, you get it here, and then we run 2 different models. So we have the lambda CDM and also the model with modified gravitational strength, and then take the difference and look up for some interesting constellations. So in the meta-dominated area, you can neglect this term here and then rewrite the total deviation in the growth rate with respect to lambda CDM and express it in terms of the area under the modified gravitational strength curve. So with some additional piece. So then we can use the relation with the growth factor with the growth rate, assuming that we don't deviate too much from the lambda CDM, and we can write make an expansion of the exponent and rewrite the deviation in the growth factor in terms of the integrated value of deviation in the growth rate, which can be expressed this way. So now we have this kind of simple relation that describes the deviation of the growth factor due to modified gravity. And so we adopt a very simple form which can be managed and understand the analytical consequences. So we introduce this G matter and the deviation from the Newton gravitational constant in terms of the amplitude and the sigma deviation and the peak of the strength. And then you can use approximate integrals and can arrive at this kind of relation, which tells you that the deviation in the growth factor is the area under modified gravity curve. So and this is a very nice thing that tells you that the thing happened in the past actually is a fractional offset in the growth factor. So, and in terms of here the plot, I depict the deviation from the deviation in the gravitational strength. This is in terms of logarithm. The x-axis is the scale factor, the logarithm of the scale factor, and you see that the growth rate is slightly damped in the amplitude. This can be traced back to this equation from this kind of relation. And then it's delayed in time in the history. So, but we also can do the numerical solution to the equation. So, and so we can look at the different quantities, so including the deviation from the gravitational strength as well as the growth rate. So as you see here, the deviation in the growth factor and the redshift distortion quantity f sigma 8. So the gravitational strength affects it, like so. You have the fractional offset here. So, and if you look at the another plot where we depict the absolute values of the growth factor and growth rate, the other quantities including the growth index, you see that under small variations of the parameters, there is slight deviation here, and you see that the growth index has deviations at the time where the modified gravity enters, and then it goes back to the the 0.55 value, which is the with Einstein gravity with lambda term. So the next thing we can do is to vary the parameters and check how good our numerical solutions to compute the deviations, and vary the parameters and see whether we can see this simple relation. As you see here, it's the deviation in the growth factor is directly proportional. Depends linearly on the amplitude of the modified strength and the duration of it. So this is pretty nice agreement with the numerical and analytical assumptions, analytical formula with some assumptions. So you can look at the redshift distortion deviation as well and compare it to analytic prediction. And as you see here, for for small areas, for reasonable range of parameters like 5-10 to 10% deviations from the Newton gravitational constant, so it really works well here in this region. And this term, for example, these dashed lines are so they deviate from the linear behavior is mostly because of the terms we neglected at the very beginning. And yeah, but we will be working on these small ranges in the area. So the next thing is to scan the whole parameter space and see where our approximation is valid, assuming that we are different redshifts. So here is the isocontrast for the redshift quantity. And so as you see here, if you restrict yourself to sigma below 0.5, you have a nice approximation for the theoretical prediction with this simple formula, and the numerical solutions are on top of each other, and then you reach some around 1% deviation for larger areas under the modification curve, under the modified gravity curve. So so this can be used, or so this will be used for parameterization for later analysis. So, and next we dealt with earlier modification and understood that it creates only the fractional offset in the observables, like the f sigma 8 or growth factor, which is proportional to the sigma 8, the mass fluctuation amplitude. So we introduced try to parameterize the late time modifications and look what happens, whether we can find some similar patterns. But as you see here, anytime you compute the growth factor or the redshift distortion quantity with these potentials, assuming that your area under the modified gravitational strength curve is the same, you see that we end up at different values here and here and here. So you have this for rising here, for constant here, and then you end up here. So in principle, you could distinguish if you somehow smartly use the outcome of the experiment and relate this quantity at least to the observations. You could probably identify the differences between the rising and falling behavior of the modification of gravity. So now let's compare the late time and early time modifications. And as you remember, we had this fractional offset for early time modification, and now we change the different shapes, different boxes, and anytime you modify the shape, whether falling, rising, you end up almost with the same value in the end. Opposite to the thing we experience with the late time modifications with power law behavior. So now we so using these quantities and also some prior knowledge and some instrumental data, we can put some constraints on the modification of gravity. So we introduced the parameter S, which includes this fractional offset and sigma 8 quantity, and the amplitude of the modification of gravity at low redshifts. That is. Oh yeah, sure. Okay, thank you. So I think I'm almost done. Okay, and these are confidence contours computed with Fisher matrix analysis. So here we put this dashed curve is the 68% confidence level with assuming the prior knowledge on S parameter. And then we, as you see, you have some certain constraints on the low redshift amplitude modification of the amplitude at the low redshift. So, and you can constrain it even further by introducing the constraints on the matter density. And then finally, if you use actual data from the DESI, provided by DESI instrument, so where they are planned to measure F sigma 8 with 2 to 3% between the redshift range from 0.05 and 1.85, you can almost approach the ellipse or the constraints given with this prior knowledge. So now, it seems that in principle you could detect this kind of 5 to 10% deviations and draw a circle for constraints and put some. So in principle you can with DESI instrument you can identify some modifications of gravity if they follow the way we in our toy model. So the next question is to ask whether we can distinguish between falling constant and rising behavior at late time. So it turns out if you look at the ellipses, these bigger ones correspond to this case. This, as you see, the falling and constant are almost on top of each other, and they don't really. You cannot really differ between falling and constant. So, but there is a strong covariance between these two parameters. And also, if you look at the rising case, so even though you can, so there is a different orientation, but still you introduce this high uncertainty, and you don't really distinguish between these three cases. So the thing you can insert additional prior knowledge, but you have to use other sources from other experiments, and probably, but we have to work on that. So this brings me to the summary. So we proposed a simple parameterization for modification for the modification of gravity expressed in terms of where the deviation is expressed in terms of the area under the modification of gravity curve. And so we showed that in principle you could detect 5 to 10% deviation from the gravitational strength, and but unfortunately you cannot distinguish between different kinds of late time modifications, the behavior of it, constant raising or falling. So this, I think this will be a subject for the next studies, and some details, some other details you can find in our paper in 2017 at GCAP. So I think. So thank you for your attention.
Thank you, Mr. Any questions? Okay, Professor Sushko.
It's rather not question, but some comments.
Sure.
In fact, you consider when you speak about some modification of gravity,
yep,
you consider very simple model, and you consider the gravitational constant as a function of A. Yes?
Yeah.
Well, and that's all.
Yeah, so this is a
Yeah,
toy
yeah,
model.
it's very simply, and you consider only you modify only equations for perturbations, and well, yeah, some Gins equations. But if you want to modify in some appropriate way, in fact, if you consider G as function of A, this is nothing but the Brans-Dicke model, and you should do it more careful. So I don't know is this approach correct or not. Probably not. So it's very simply, and you lost some maybe important points this using this model. So it's command, but if
Yeah,
you
sure.
if you want
it's purely valid.
you can answer and reply.
I don't pretend for generality, but I know that there are so many papers in. So I mean that the modified gravity papers are so the reviews are more than 250 describing different kinds of models, and it is nice to have some. You know, this even though this model is incorrect in purely mathematicals.
You just take the equation for perturbations. And
yeah, these are.
Input this modified gravitational constant in this equation.
Yeah,
but this equation should be derived from the very beginning. From the basic model.
Yeah. So the point is,
I don't think that this equation will keep its form after this.
Yeah.
Professor Stabinsky?
About it. It just indeed I wanted to say approximately the same, but in a more constructive way. And actually, I even would like to propose your some people if you are interested. The statement is indeed in almost all modifications of gravity, your equations for dust matter perturbations will have though similarly the same form, but with the curve the factor depending not only on A but on K2 on scale. And so indeed, and actually that's why it would be much more interesting to consider the relative change of the growth factor at two different scales. So that's why they restrict ourselves only say to F multiplied sigma 8 and not to F multiplied sigma E16, for example. I proposed this problem actually a number of times in the past to young scientists, but their answer was it is difficult. Okay. But once more, what was difficult in the past may become well possible in the now, and so I would say even the simplified form of my proposal is to try to look at the existing observational data not only at 8 megaparsecs, but at 16, say, twice more. It's twice more scale, it's twice larger scales, and compare the growth factor at this two scales, and this will I'm sure that this will make possible to exclude a very large class of possible modifications of gravity.
Thank you for your comment, Professor Song.
Yeah, also very quick comment. So I understand you actually met 2 months ago in the Kazi. I think it's the first cosmological paper you produced. It's amazing, the progress. And then the one thing is that probably you can discuss with the the Eric later, I
Mm-hmm.
totally agree to the source code. So it's the phenomenological finds are more realistic.
Mhm.
So I actually look into some the general behavior of the theoretical model, and you actually will find eventually at least you need to introduce two parameters like some the delta G. Also, the gravitational anisotropy is always induced. It's like it's coupled, they connect to each other. So I think that probably we can discuss, make a little bit some the more.
Okay.
Yeah.
Thank you. Thank you.
Thank you, Professor. Any comments? If not, okay. Thank you,
Mhm.
Misha.
Thank you.
The next talk is Bobinski from Poland. Okay. His topic is about the investigation of alignment of galaxies in clusters and photos of methods and results of research. Hold on, please,
Which is this? Yes. Yes. It is my pleasure to present the doc in investigation of alignment of galaxies in clusters. The problem is that one of the most important problem of the present cosmology and extragalactic astronomy is the problem of the structure formation. In the commonly accepted Lambda-Coordinator model, the universe is deemed to be spatially flat, homogeneous and isotropic and appropriate scale. However, the dimension of this scale was changing with our growth of knowledge of the universe. You know, of course, very well these pictures. Why we investigate angular momentum? It is because various moment accounts for various aspects of galaxy formation process, of course. And of course in different scale. As well, as the various observations give different informations. What is most important that the different models give different predictions about angular momentum of galaxy and their alignment. So, in other words, the observed variation of angular momentum give us simple but fundamental test for different models of galaxy formations. Most important, it is the more main model of galaxy formation. Most important are hierarchical clusterings. In this moment, structures was formed in the universe from bottom to up as the consequence of gravitational interaction between galaxies. Second model is Zeldovich-Pankage model. Structures in the universe forms from bottom, from up to bottom, as the effect of antisymmetric collapse of large structures. What is also important, Lixing-Lee involves a model in which galaxy forming in rotation universe as a consequence of the conservation of angular momentum in rotation rotating universe. Different models, different theory of galaxy formation made different predictions regarding the angular momentum. It's the most important paper. So, for example, in primordial turbulence, we have angular momentum oriented perpendicular to main plane of the structures. In the Zeldovich-Pankage models, they are parallel, but in the original hierarchical clusterings, it should be random. But later it was shown that model of hierarchical clustering was improved for the mechanism of the tidal torque, so it's named tidal torque scenario, and also recently was an effect of the micropancake. It is the, in fact, Zajdovich pancakes, but is working not in large scale, but in the small case. First conclusion from the order papers is that the orientation of galaxies in the local supercluster is in agreement with the Zajdovich pancakes models or with new variants of the Tiger-Talk scenarios hierarchical clusterings. What is the base of the investigation? Few words. We're assuming that galaxy or galaxy structures is three-axial ellipsoids. So now we could compute the angles given the spatial orientation. First, of course, is the position angle. However, analysis only the position angle gives the information about angular momentum only for on galaxies. Second possibilities is to compute two from the inclination angle and position angle, and of course the position of the objects, two angles. Delta D giving information about inclination, normal to the main plane of the coordinate system. And second, angle eta giving information about location of the projection of this normal to the main plane. It is theoretically is much better, but we have two difficulties because what is the true shape of galaxies, and moreover we received two solutions like that and like that because we're based on projection. For this analyzed, we use the methods which introduced by Havley and Pips. They give the proposal, they used three statistical tests for investigation of galaxy orientation in the large-scale structures. In fact, in this method, we investigate distribution of the angles giving information about angular momentum. The situation was that if we are going from the rather alignment in the different structures of galaxies, that we start with paper Godlowski, Szydłowski, and Trin, suggested that the pairs and small groups have like non-vanishing angular momentum. For the groups and poor cluster, we have no alignment, and again we have alignment for the more massive structures. Also, it was very important to say that it is assumed, of course, that normal lines to the galaxy plane is the verse axis of rotation, which seems to be quite reasonable at last for the spiral galaxies. Alignment of galaxies in cluster increased with the number of objects with particular clusters. It was investigated in details in our previous papers. Usually this dependence is presented as the formula, and it was theoretical problem. It was many attempts to explain this relation. However, in the light of the models of galaxy formation, survive only two possibilities. Alignment is due to the Tiger-Talk, as suggested by at first in Catalan and Tens, and it was also analyzed in our latest paper. And second possibility, it is the Dixon-T model, so it means rotation of the universe. In this theoretical result from our paper with Professor Stefanowicz is that we applied the statistical methods from Chandrasekhar used there to calculate Fourier-Holzmark distribution. The main differences with the previous papers is that we reduce the problem to the discrete many-body case, where all physical properties of the system are determined by interaction potential. We show that with reasonable assumption about cluster morphology, the angular momentum of galaxy structures increased with richness. However, the final form of this dependence depends on the assumption about cluster morphology. And moreover, we show that angular momentum of galaxies increase with time. However, so it's also possible to test it. However, present data with the about galaxy clusters of galaxies is not sufficient to test in observationally. In fact, but with new project also was discussed in this conference, we hope that it should be possible. This conclusion is that this classical relation is predicted by the Tyler-Torquist scenario in hierarchical clustering model and in the model of the link D. In our paper, we say that it's not necessary to the power 5/3, but it could be also different, but it depends on the model of the formation of the cluster. Maybe it should be point that Dixing model predicts is very interesting, but predicts wrong amount require the rotation of the spiral galaxies. So it is the value the same as obtained before by Birch, but of course we know that it is contrary to the quadrupole momentum of the CMB. However, it is one possibility because to tell you the truth, Dixing model was working not only in the rotating universe, but also if we have not necessarily general, but large scale rotation. 2 months ago, I was on the conference and I found that, for example, Professor Malec was working in such theoretical models. What's happened with alignment of the galaxies in cluster? We based on the catalog of the cluster by Pankov-Lin. The advantages of this catalog is that we have no, in fact, background objects at misclassified galaxies. The most important result of the first paper is that from observational point of view, that values of analyzed statistics increase with amount of galaxy members, which could be interpreted as relation between anisotropic number of galaxy clusters. But I introduced the new method of alignment in cluster because the question is not only if it is increased, and if it is real alignment in such type of the cluster. I take the test original introduced by Pips, give the mean value for sample of 247 Abel clusters, and compare the mean value what I obtain with theoretical prediction. This is origin. However, the situation is, of course, this first test is chi-square test, second is autocorrelation test, was introduced by Peace, but he say some oversimplification that we have that all solution is not dependent to each other. However, in fact, in autocorrelation test, we have polynomial distribution, what will give some changes in the mean value. Of course, for one cluster is not absolutely not important, but if we have sample for more than 200 clusters, of course, it is valid. This similar situation is from the Fourier test because a result of a Havley-Prips was obtained from theorem of propagation error. It means linear approximation. But of course, amplitude, this formula is strictly nonlinear. So we should, of course, give some computation. Now, of course, I haven't time to give it in details, but it's modification both in the mean value and in the standard deviation. And of course, again, it's not important for one cluster, but for a huge number of the cluster sample is very important. The result of analysis is that we found that the orientation of galaxies analyzed clusters are not random. Here, it means that we found existence of alignment of galaxies in our sample. But next problem was that usually, because it's the much more simple, used the position angle as was originally proposed by Jim Phillips. But if we take the spatial orientation, we found that the distribution is different. Why it is? And because if we analyze the spatial orientation, usually we don't know if the galaxy, because we have projection, if we have such situation on this. So we have two solutions, and the people rather, of course, know about it, but think, oh, it's not important because they are independent. But in fact, it's of course not independent, because if it's face on, it's very closed, but for H on, is possible very different. It must be so. It's all statistics are modified. It is one more example. The conclusion is that alignment of galaxies in clusters increase with the number of the objects in particular clusters, and depends between angular momentum and cluster richness is in agreement with target scenario in hierarchical clustering models and with the thinking model. Because till now, the model Zerdowicz model is not predict increasing with richness. However, you know that Zerdowicz model now is only very few people is working. So, what's with changing with Bouts-Morgan type of the cluster? It is the result from different type of Bouts-Morgan clusters. And conclusion is that one should note that only for cluster type Bouts-Morgan 2 to 3 means deviation from case when the cluster have other morphological type, and also deviate from the mean value from the whole sample. Conclusion from discussed paper, but the statistic methods used for the investigation of galaxies alignment were improved, and the new method of investigation of alignment of clusters was proposed. The group of galaxies in an alignment is not observed, for which able cluster alignment is observed. Also, the new paper of Lee was published, I don't think, about 1 year ago, also compare that from analysis of gravitational grenzings, confirm that for the pair galaxies we obtain alignment. Alignment of galaxies in cluster increase with the cluster richness. Galaxy alignment of the locality also for location inside or outside the supercluster and supercluster richness. So it means that we have environmental effects. But when we analyze cluster with different Bouts-Morgan type, possible difference is observed only on the case of the Bouts-Morgan 2 to 3 types. And moreover, we show that angular momentum of galaxies should increase with time. However, it is not possible to give results now, but we hope that in the near future it will be. General conclusion is, in the commonly accepted lambda coordinate matter model, the structure were formed in the perimeter adiabatic nearly scale invariant Gaussian random fluctuation. No present scenario of galaxy formation explain all observational result, but recently improvement hierarchical clustering model, radiator scenario with including effect of micropancakes, correctly predicts both alignment of galaxies in structure and dependence of alignment with mass of the structures. The alignment of galaxies in local superclusters, so is very near, is also with agreement with this result. And of course, we have also we are sure that environmental effects is also important. Thank you for your attention.
Any questions? Professor Chechen? No. Okay. Thank you, Professor Gladlowski. And the next talk is of Professor Chechen from Peskov University, Peskov Institute, and his talk is about topic is bathing the universe rotation.
Все пойдет, да? Будь добр, show me the presentation. Нет, она там стоит. No.
Find alignment even for quasar. And of course, no
New step. Там называется new step. Ага. Dear colleagues, I present my new report at the Nazarbayev University. The title is New Step on the Argumentation of the Universe Global Rotation. What I want, first of all, I want to say, the problem of universe rotation is very important, and maybe it is very dramatic for modern cosmology, and a number of scientists consider this problem from opposite points of view. Some of them say that there is no rotation of the universe, and others say that we have the rotation. That is why it was necessary to consider this problem from a more general positions, and that is why we formed the special scientific collaboration for preparing special ICU. This ICU have been published this year. Где это? This ICU have been published this year under the title The Universe Rotation, Pro and Contra. Some people say that this we have a universe rotation, others said that there is no. I'm repeating, but nevertheless, you see, in this collaboration, a number of famous scientists, astronomers. First of all, this is Professor Godlowski. He said, by the way, the scientific editor of this book is Professor Murzakulov from our Eurasian University, and so on. So, for explaining my point of view, we see that there are two approaches for description of the universe rotation effect. First of all, this may be explained on the basis of so-called Bianchi types of universe, and other side, it is possible to consider the universe rotation on the basis of Papa-Petro equation. We talk about only about the spinning part of the Papa-Petro equation. In this slide, you see some results of Planck mission, and what is the result of this mission that connect with the process of universe rotation? Does the universe rotate, or it doesn't? It doesn't rotate, and they found the ratio between universe angular velocity with respect to Hubble constant, you see, is very, very small, and this result have been got with confidential level at 95%. That is why the question arises: why this effect is very small, and for examining for very short way for examining of this process, I used the well-known gravitational analog of Faraday rotation, and I used the process of light rays torsion, and if it's so, it is possible to calculate the angle of polarization plane rotation for these light rays, and as the result we see this is torsion K, and the angle of plane polarization rotation describes the following expression. It depends on density of the universe, time living of the universe, and angular velocity of the universe. And basing on this result, it is easy to see that ratio is possible to express. It will be directly proportional to this delta phi, and delta phi, this is angle of rotation, and we know that in expanding universe, all physical processes determined by temperature, but determined by temperature fluctuations. And if we see take into account the magnitude of temperature fluctuation, delta T divided by T is order 10 minus 8 minus 9, then we can, in crude approximation, conclude that omega divided by h is about 10 minus 8, 10 minus 9th power. So in this case, we see the correspondence of these results with results that have been found in the Planck experiment. But nevertheless, it is very important to put forward another question. Why, first of all, why it's so, and maybe it is possible another way for estimation of this ratio. For understanding the process of universe rotation is possible to consider two variants of gravity theory. This is classical Newton theory and the general relativity from other side. And if we are considering the process of universe rotation within the framework of Newtonian theory of gravitation, it is necessary to use the equation of rotation. This is equation of rotation, but potential depends on vacuum potential, and that is why, as a result, we get the following expression: omega v. This means rotation with respect by vacuum, and we get the following result: omega 0 L divided by R0. L, this is sizes of any body. R0, this is distance from observer to the center of this body, but omega 0 describes by following expression. And if we use this formula for describing universe as an entire universe, it is necessary to put that L equals R0, and the result will be about 10/19th in 19th power hertz. That is why we see that in principle ratio between omega 0 and Hubble value becomes approximately equal to 1. Really, Gamov put forward an idea that ratio between omega and h equals to 1. And moreover, he put forward the idea that universe rotates, and the reason of universe rotates is the same that reason for the universe expansion, and that is why he put forward ratio. He put forward expression that this ratio is about 1. But how it is possible to prove or maybe consider from other side? I said that my previous results were considered in the framework of Newtonian gravity, but it is possible to consider, it is necessary to consider this problem in the framework of general relativity. And for doing this, I show you the equations that have been used by Chagas 3 years ago. This is well-known Friedman equations, and this equation for omega. But earlier, I put forward more complicated expression, system of equations. This is usually Friedman equations, and this is spinning part of Papa-Petro equations. But what is the difference between this one and this one? In this case, we are considering the variable Hubble constant. And what will be the result? What will be the result? Basing on this result, it is possible to reinterpret of Planck experiment. For example, we consider the case when the universe only rotates. Some time ago, Zeldovich put forward very simple case for calculating the Hubble constant. He considered any ball on the surface of which we have any particle. This particle describes the galaxy, and in the case of equality potential, kinetic energy and potential energy, basing on this result, we get the Hubble constant. Basing on this idea, Zeldovich idea, it is possible to complicate this expression by including kinetic energy, potential energy that depends on universe rotation. And for simplicity, for future calculations, I omit this term and have deal only with this one. And the result is as follows. We get another expression for Hubble constant, and you see this Hubble constant equals 1.2 multiplied by omega v. That is why the ratio between v and h approximately equal to 1. Next step. Hubble constant from Planck experiment, as you see, depends on number of physical mechanisms. First of all, it depends on density of dark matter, number of neutrinos, and so on. That is why maybe Hubble constant also consists of number of components that allowed to consider the process of universe rotation in details. So let's consider another case, universe rotation with connection with gravitational lensing. For us, it is very important the following. If that we have not only number of images as you see in this figure, this is images of any quasar. This is image of any galaxy. But very important for us is that these images located at different distances. And what is the result? Let's consider the crude scheme of such situation. We have lensing galaxy. This is lens, and we have two images, G prime and G2 primes. And let's consider the simplest case when universe only rotates, and that is why galaxy G haven't radial velocity, but its image possesses by radial velocity. Sorry, this scheme is not correct. It must be, it must be directed along this line. But it is easy to understand that image, because G and G prime, these 2 points lays on the picture pattern that pass through these 2 points, and it is possible to calculate. It is possible to calculate this radial component. So, basing on these results, it is possible to calculate it. As I said, it is possible to calculate its radial velocity. Its radial velocity dv. It will depend on distance. It may be luminosity distance, universe rotation, magnitude of the universe rotation, and Einstein angle. After some calculations, we see it is possible to calculate omega if we are knowing the mass of galaxy or galaxy cluster, luminosity distance, and by Doppler effect it's possible to calculate the dV. And after some mathematics, we get the relation between universe rotation omega and Hubble constant. This is expression. This must be sign of proportionality. 2.5 divided by 1 divided by z squared multiplied by h0. And this is very important result because if we consider the concrete quasar that locates at distance or redshift 1.6, we get that omega approximately equal to 1. For more larger redshifts, about 10, we get that omega is about 10 minus 1 minus 2 of Hubble constant. That is why. What is the difference between Planck results of Planck experiment and these calculations? It depends on the following. Planck experiment have been done by searching the process of rotation of microwave background radiation. And due to its smallness, the result, of course, very small. But if we consider more precisely the Hubble constant, it is possible, from my viewpoint, it is possible to consider the case when universe rotates with more large velocity. But what does it mean, large velocity? This is for our everyday life. Of course, this is very small, but nevertheless, in cosmological scales, it is necessary to take into account. That is why, as a conclusion, I must say that for understanding the process of universe rotation. Does universe rotate or no? It is necessary more precisely examine the Hubble constant. That is all.
Thank you, Professor Susan. Any questions, comments to Professor? Professor Godlowski, please.
I have short comment. May you show your transparency 13? 13.
13.
Yes, it is. I think that is very important because, of course, in the present moment, is not necessary, but it is potential possibility of testing rotation.
Yeah.
Because this parameter Hubble constant is not obtained directly from the Planck, but is the multiple factor of matter.
Absolutely
yes.
right.
So. Now it's imperfect, but if it will be differences for that parameter obtained from the microwave background and supernova, it is possible to explain. We show when a few years ago, before Planck's, when there was some tension with the result between the double map and supernova, we show that for this tension is possible to explain by dark radiation. So it means because it's the three similar effects, Casimir effects, rotation, and the brain effects. So, of course, in that moment is perfect agreement, but with specific cosmology, where the error bars will be smaller, it is possible that it will be again important.
Thank you. Thank you.
Okay. Magjan, please.
Excuse me, I think I missed the part when you were explaining the axis of rotation. Can you...
What?
The axis of rotation, if universe rotates, it needs to be rotating about something or not?
I don't understand. What do you mean? What do you want to ask?
Probably, if I understand you, the problem is that in the Newton universe, we have, if we have rotation, we must have axis, but in the general relativity, we have no axis.
The deal in that due to the vacuum, vacuum is the reason of universe rotation, and moreover, due to vacuum, every cosmic object that locates in the universe possesses by initial rotation, and maybe this will be the reason of that process of alignment of momentum of galaxies, about what said Professor Godlowski. That is why in any essence, it is possible to detect the direction in the sky along which momentum of a number of galaxies they are alignment along which, and the question arises: is it possible to say that this is axis of rotation, or it may be another interpretation? Because when we are considering the very early universe on the basis of Papa-Petrov equation, its spin. Initially, this is microparticle with any spin, and its spin, due to its chaotical movement, have arbitrary orientation. And how it is possible to consider the direction of this axis at our day? Of course, this is very difficult question, but nevertheless, it may be any direction. That is why this is my answer. Sorry.
Any questions, comments? If not, okay. Professor J, thank you for your presentation. It was the last.
Спасибо.
Of this session.
Совсем.
Before the round, announcement about the Borovoy, and it will be special sessions at Borovoy. It will be at 10 and 11th August. Huh? Sorry? Okay. With touristic booths, yes, of course. So, um, oh, okay. So,